In the last video, we talked about how to find the determinant of a 3 by 3 matrix by using cofactor expansion and finding the determinant of several 2 by 2 matrices. So you might be wondering, what is that all for? And that's really for what I'm introducing here, which is the cross product of two vectors. So I'll introduce this by giving another physical application, which is torque. So compare this to work, which we looked at earlier, which the dot product was very helpful for. Work was a scalar quantity. It just had a magnitude, but no direction. You can't do work up or work down. It's just work. Torque, on the other hand, you may have heard this term before. You may have worked with this. You may have seen a similar situation as this one, where we have a bolt and a nut on that bolt, and then we have a wrench attached to the nut. And the idea is, if we apply a force to that wrench, it may have the effect of either tightening or loosening that bolt. So, question is, how much does it tighten or loosen the bolt? What does the effect of that force have on this system? What will happen to the bolt? So, a couple things here. The bolt could either go in, the nut could go either in along the bolt, tightening it, or it could go out, loosening it. And so what that's telling us here is torque has a direction. I'll say here has direction. And then, of course, it also has a magnitude, the amount of twisting effect that it has. If there's a lot of friction, if it's a really tight bolt on here, you're going to need to apply more force to have it screw in or out. And if it's, maybe greased up, something like that, you'll be able to apply less force to get the same effect. So it has direction and magnitude, and therefore torque is a vector. So what we're talking about here is taking, there's sort of two things that go into how much torque and in what direction the torque will be applied. One of those is the lever arm here, the length of the wrench and also the direction of the wrench. We need to also have that information. So that is our R here. This is the vector describing both the direction and the length of the wrench, or in general, just the lever arm. So you don't have to be tightening a bolt. You could be, say, trying to move a rock, something like this. But anyway, so we take two vectors. R, that's the wrench, that's a vector, and our force that we're applying to the wrench, F. And this length of R, what we're really talking about here is not just the length of the wrench, but rather at what point we're applying the force to. So if I move this force down to, say, here, my R would no longer go all of this way. My R would then turn to here. So this R is really describing the relationship of the force to the lever arm, the length of that lever arm. So we take two vectors, and we know what comes out, torque, which we use a tau symbol to indicate, is also a vector. So take a vector and another vector, lever arm force, and output another vector, which is torque. And that torque can either go in along the bolt or out along the bolt. So there is some direction to the torque. It seems like it's always going to be parallel to the bolt, and that is true. But nevertheless, it has a direction. So how do we determine this? Well, in the case of work, remember, we were interested in the amount of force that was parallel to the direction of motion. It meant we had to break down the vector and just look at how much of it went in the direction of motion, that was parallel to that direction vector. Here, with torque, it's a little bit different. If I just think about if I apply a force to this wrench in the direction of the wrench, well, that's going to have no twisting effect. And so what we're really talking about here is some sort of kind of an opposite of work. Rather than caring about the amount of force in the direction of the lever arm or the wrench, we actually care about the amount of force perpendicular to the lever arm. So that would be this vector here in green. This is the component of my force vector in the perpendicular direction to the lever arm. That's what we want to get a hold of. And from physics, you can do some experiments and find out that the amount of torque generated is proportional to the amount of force in the perpendicular direction multiplied by the length of the lever arm. And so it's actually not just proportional to that, but actually exactly that. So this component of F, component of the force in the perpendicular direction, that's going to be magnitude of F sine theta. Why is that? Well, theta here is our angle between the force vector and the r vector. If I take this force vector, for instance, and I'm not applying the force down here, but if I just take this force vector and I move it down here, and I just kind of look at it down here, where the nut is, we will have this angle theta here. That's the same angle theta here. And then just using some trigonometry, this will be that same angle theta. And now we have a right triangle, because I'm talking about the perpendicular to r. So we'll have a right triangle. This is our theta. And so F sine theta will be this length. So this length is F sine theta. Magnitude of F times sine theta. And then, physics tells us that the amount of torque then, so just the magnitude of the torque vector, is equal to the length of the lever arm times the magnitude of F times sine of theta. So that just tells us the magnitude of torque we get by doing this calculation. But remember, torque also has a direction to it. And so whatever this operation is that takes in the lever arm, takes in the force, outputs a torque vector, it's also got to tell us the direction of that vector. Now, the direction of that vector we get by doing what's called the right-hand rule. So take, for instance, this system that we have here with all of the vectors as they are. So what you do is point your fingers in the direction. So this is your fingers. Point your fingers in the direction of the lever arm. So notice you can do that two ways. You can either, well, a lot of different ways, but you could either go sort of palm down or palm up. So how do you decide whether you do palm down or palm up for that? Or maybe a different direction. The idea is point your fingers in that lever arm and then curl your fingers in the direction of F. So in this case, it's pointing sort of downward. So in order to curl my fingers downward after having my fingers, my right hand, again, this is the right hand rule, my right hand fingers pointing along the lever arm, if I curl them downwards, my thumb is going to be pointing along the bolt. That'll be my thumb. So, right, so fingers this way, and then curl these downward with the force. So this will be like the direction of my palm or the curling. This is my fingers. So fingers across the thing, palm down, my thumb points in along the bolt, which means this is going to have a tightening effect. This torque is going in. That's what's going to happen in this torque, or I'll say direction of torque is in along the bolt. So that is, it's parallel to the vector that describes the bolt, and it's going inward along the bolt. So that has a tightening effect. So, and then let's try it slightly differently. So change this. Maybe I'll use this cyan. So let's say instead of pointing this force downwards, let's say I move the wrench upward. I apply a force from the bottom of it to up. So now I point my fingers in order to curl them upward. My palm should be facing up, and then when I do that, my thumb is pointing instead of inward along the bolt, it's going to be outward along the bolt. And that's going to have a loosening effect. So one of those two things has to happen, depending on this force, or maybe nothing if I'm completely parallel to the lever arm. Nothing will happen, so it's possible I get a 0, which remember is a vector that has no direction. It's our one vector, so it's possible that could happen. We could tighten it, or we could loosen it. So of course, there's the saying righty-tighty, lefty-loosey. You can sort of, I guess if you like that enough, you can think of it righty-tighty. I'm going around like this, it's going to tighten it. But rather, in this class, you can start to think a little bit harder about that. I never liked the righty-tighty, lefty-loosey because it's right isn't well defined for a circular type motion. Are we talking about right from the top or left from the bottom? Those are the same thing. So the bottom's moving left, the top's moving right. That's going to have a tightening effect. The bottom moves right, the top moves left. That'll have a loosening effect. So it's kind of, to me, it was always a little bit confusing, and it wasn't until I had a Calc 3 class, or rather my AP Physics class in high school, that I sort of, instead of thinking righty-tighty, lefty-loosey, I just used the right-hand rule. Curl your fingers in the direction of this circular motion. Curl your fingers in that direction. And the way your thumb is pointing tells you whether you're tightening it or loosening it. In to tighten, out to loosen. So that's the idea. We have this magnitude, and then the direction is determined by the right-hand rule. All right, I'm going to sum all this up in one slide. This is the cross product. So cross product is this operation that takes the force vector in the lever arm and outputs torque. So let me just make a note of that here. This torque we get by doing R cross F. And so in general, we don't have to be doing torque. In general, we take two vectors, although torque is the thing to keep coming back to have a sort of visual for this. Take two vectors, u and v, in 3 dimensions. We got to be in 3 dimensions for this. Cross product, u cross v, has magnitude, as I said, magnitude u times magnitude v times sine of the angle between them. And then the direction of u cross v, because remember this is a vector, is given by the right-hand rule. Point your fingers of your right hand in the direction of u, curl them in the direction of v, and your thumb will point in the direction of u cross v. Now, and a really important thing to notice here, and I'll hit this early with the cross product, u cross v is always orthogonal to both u and v. That is, it's perpendicular to both u and v. So go back to this picture here. I have my force, I have my lever arm. I can make a plane, if I want, out of those vectors. So let's take this as our force again. So I can sort of form this plane here, where my lever arm and my force reside. They're both parallel to this plane. The torque vector will be perpendicular, normal, or orthogonal, all meaning the same thing of being perpendicular to that plane. And what that means is that the torque vector, or the cross product in general, is perpendicular to both R and F. Or, in the case in general, perpendicular to both u and v. So these are the big things. When we define a new vector operation where the output is a vector, we need to know how much, what's the magnitude of that vector, along with the direction. And these are both given here. And then the other big takeaway here is the cross product is what gives us torque. That's our motivation for understanding the cross product, although we'll see other applications of it. All right, that's it for this video. I'll see you next time.